For more than 30 years, humanity has been finding new worlds around other stars, almost entirely in the dark, without ever actually seeing them. We have cataloged nearly 6,000 exoplanets since the early 1990s, yet the vast majority of them exist to us only as numbers on a spreadsheet, inferred rather than observed. That changed in the summer of 2025, when the James Webb Space Telescope did something it had never managed to do before in its entire operational history. It looked at a patch of sky, and it actually found a brand new planet with its own eyes, using nothing but the faint heat glowing off that planet's surface. If that sentence doesn't sound remarkable yet, stick around, because by the end of this video, you'll understand exactly why scientists are calling this one of the most important exoplanet discoveries of the decade. And if a moment in this story genuinely surprises you, that's your cue to smash like and hit subscribe, because this channel is where real space discoveries get explained properly. To understand why this discovery mattered so much, you first need to understand just how hard it normally is to actually see a planet orbiting a distant star. Picture trying to spot a firefly hovering a few feet away from a lighthouse beam at night from miles offshore. The lighthouse doesn't just outshine the firefly, it completely drowns it out. That is essentially the problem astronomers face every single time they point a telescope at a star system and try to find a planet. Stars are staggeringly bright compared to the planets orbiting them, and that brightness difference only grows worse the closer a planet sits to its star. This is precisely why, out of the thousands of confirmed exoplanets we know about today, the overwhelming majority were never actually photographed at all. They were detected indirectly, through clever workarounds that infer a planet's presence rather than capturing it on camera. The two most common indirect techniques are worth understanding, because they explain why direct imaging is such a different beast entirely. The transit method works by watching a star's brightness over time and waiting for a tiny periodic dip, the kind of dimming that happens when a planet crosses directly in front of its star from our exact vantage point in space. The radial velocity method takes a different approach, measuring the subtle gravitational tug a planet exerts on its host star, a tug strong enough to make the star itself wobble back and forth ever so slightly. Both of these methods have been enormously productive, responsible for finding thousands of confirmed worlds between them. But neither one actually shows you the planet. You're reading its fingerprints, not seeing its face. Direct imaging is the opposite of that entirely. It means capturing actual photons of light, or in this case, infrared heat, that traveled from the planet itself all the way to our telescope's detector. And prior to this discovery, despite everything the James Webb Space Telescope had already accomplished since becoming fully operational back in 2022, it had never once managed to find a brand new planet this way. The tool that finally made this breakthrough possible is called a coronagraph, and it deserves a moment of genuine appreciation, because it is a stunning piece of engineering. Think of a coronagraph as a precision-built light-blocking mask purpose-designed to suppress the overwhelming glare pouring off a star so that far fainter objects nearby, planets, dust rings, faint companion stars, actually have a chance of being detected at all. The specific coronagraph responsible for this discovery is installed on Webb's mid-infrared instrument, known by the shorthand MIRI, and it was designed and physically built in France. A critical piece of hardware contributed to the observatory, specifically to make this exact kind of observation possible one day. Even with that instrument in place, actually pulling off a detection required an enormous amount of careful image processing after the raw data came back down. Researchers had to subtract out the residual glare that still managed to leak past the coronagraph's blocking mask, isolating whatever faint infrared signal remained underneath. When that processing was finally finished, something appeared in the data that hadn't been there before, a clear, distinct source of infrared light sitting near a young star, completely separate from the star itself, sitting exactly where a hidden planet's heat signature would be expected to show up. Here's where this story stops being pure astrophysics and starts becoming something closer to genuine detective work, because the research team did not simply get lucky, pointing a telescope at a random star and stumbling onto a planet by accident. They had a specific, informed reason to suspect something was hiding there long before Webb ever confirmed it. The star in question, catalogued as TWA7, is remarkably young, only around 6.5 million years old, essentially a cosmic infant when you compare it to our own sun's 4.5 billion years of age. Like many young stars, TWA7 is surrounded by what astronomers call a debris disk, a wide, flattened ring made of leftover dust, ice, and rocky material left behind from the star's formation, the same basic raw material that gradually clumps together over millions of years to build planets from scratch. When astronomers first studied the structure of this disk using ground-based observations, from the European Southern Observatory's Very Large Telescope in Chile, they noticed something worth paying attention to. The disk was not a smooth, uniform ring at all. It showed distinct structure, including a narrow, relatively empty gap carved into the material at one very specific distance from the star. Gaps like that do not typically appear on their own, and this is honestly one of the more elegant pieces of reasoning in modern astronomy. The leading explanation, built on decades of studying how planetary systems form and evolve, is that something with real gravitational pull, a planet, is orbiting directly inside that gap, its gravity sweeping the surrounding dust and debris clear as it moves, carving a path through the disk the same way a plow carves a furrow through an open field. So when the research team, led by astronomer Anne-Marie Lagrange of the CNRS in Paris, finally turned Webb's coronagraph toward TWA7, they were not searching blindly at all. They were looking at one specific predicted location, mapped out in advance by the physical structure of the disk itself. And exactly where the math said something should be hiding, Webb found it. The newly confirmed object, designated TWA7b, turned out to have a mass roughly similar to Saturn, somewhere in the neighborhood of 100 times the mass of Earth, based on the team's careful analysis of its brightness and estimated temperature. That single number matters more than it might sound like at first. Here's why it should genuinely surprise you. Every planet previously discovered through direct imaging, stretching all the way back to the earliest successful attempts in the mid-2000s, has been significantly more massive than this new discovery. Direct imaging has historically only been capable of finding the biggest, hottest, most luminous planets out there, worlds several times heavier than Jupiter, usually sitting far enough from their stars that the glare problem becomes just barely more manageable. TWA7b, at roughly a third of Jupiter's mass, is officially the lightest planet ever successfully captured through direct imaging in the entire history of the technique, 10 times lighter than anything ever imaged this way before. That is exactly the kind of shocking leap forward this channel exists to cover. So if this is landing for you, go ahead and like this video and subscribe right now, because there's a lot more of this story left to unpack. NASA and the research team have been remarkably clear about why the specific milestone matters so much to the wider field. This is not simply one more planet added to a growing list. It's proof that our instruments have crossed a genuine sensitivity threshold, opening a door toward directly imaging progressively smaller, cooler, less massive worlds than anything direct imaging could reliably detect before this point. Worlds that edge closer, generation after generation, toward the size and mass range of rocky planets like our own homeworld. It is worth pausing here to be precise about where the science actually stands right now, because responsible reporting on a discovery like this has to include some honest caveats, and that honesty is exactly what makes this story credible rather than exaggerated for views. As of the original publication in the journal Nature back in June of 2025, the research team described TWA7b as Webb's likely first direct imaging discovery, with the object's characteristics, its position relative to the disk's gap, its estimated mass, its estimated temperature, all strongly consistent with a genuine planet rather than some kind of background contaminant, like a distant galaxy sitting behind it by coincidence, or a foreground object like an asteroid drifting through the frame at exactly the wrong moment. The team actually ran the statistics on that exact possibility, calculating that the odds of this signal being an unrelated background object were extremely small. But confirming a discovery like this with full scientific certainty typically requires additional follow-up observations stretched out over time, tracking the object's motion across the sky to verify that it is genuinely gravitationally bound to TWA7 and actually orbiting it the way a real planet would, rather than simply sitting in the same patch of sky by pure coincidence. That confirmation process has continued in the time since the initial announcement, with astronomers increasingly treating TWA7b as one of the most promising and best supported direct imaging candidates ever found. And even as the broader scientific community continues refining and double-checking every detail, what makes this discovery resonate so far beyond just one single planet is what it represents for the entire future of exoplanet science. Since becoming fully operational in 2022, the James Webb Space Telescope had already completely reshaped how scientists study planets beyond our solar system, but almost entirely by characterizing worlds we already knew existed. Its extraordinary sensitivity was being used to analyze the atmospheres of previously discovered exoplanets, identifying specific molecules floating within them, mapping out rough temperature patterns, refining our understanding of planets that had actually been found years earlier through those older transit or radial velocity methods we talked about earlier. TWA7b represents something categorically different from all of that work. This was the very first time Webb had gone looking for something new and actually found it, using nothing but the light, or in this case the heat, that the planet itself was quietly giving off into space. Sasha Hinckley, an astronomer at the University of Exeter who has worked extensively with Webb's imaging capabilities, has described this particular moment as a genuine turning point for the field, noting that reaching into the mass range represented by TWA-7b required imaging performance that pushes right up against the theoretical limits of what the observatory's optics were originally designed to achieve. In plain terms, Webb was not simply lucky here. It performed right at the very edge of its engineering capability, and remarkably, it actually worked exactly as hoped. And there is a deeper reason astronomers care so intensely about proving that this particular technique works reliably at these lower masses, one that connects directly to the single biggest unanswered question in the entire field of exoplanet science today. Every method we currently use to search for potentially habitable, Earth-like worlds around other stars comes with real, frustrating limitations baked into it. The transit method requires a planet's orbit to be almost perfectly aligned so that it passes directly in front of its star from our exact vantage point here on Earth, a geometric coincidence that quietly rules out the vast majority of planetary systems across the entire galaxy, simply because their orbital planes don't happen to line up with our line of sight, the radial. Velocity method struggles increasingly as a planet gets smaller and lighter, since the gravitational wobble that a small, Earth-sized world induces in its host star becomes extraordinarily subtle, sitting right at the very edge of what current instruments can reliably measure at all. Direct imaging sidesteps both of those frustrating limitations, at least in theory, but only if the technology actually exists to detect something as faint as a small, cool, rocky planet sitting relatively close to the overwhelming glare of its own star. TWA-7b, sitting at roughly a third of Jupiter's mass, is still a long way away from a true Earth-sized world in terms of raw mass, but it represents real, demonstrated progress down that exact ladder, hard proof that each new generation of instruments and processing techniques is inching the boundary of what's directly detectable further and further toward the smaller, cooler, rockier worlds that matter, most in humanity's long search for potentially habitable environments beyond our own solar system. There is also something genuinely worth sitting with about this method itself, completely separate from the raw numbers involved. Every other technique for finding exoplanets tells you about a planet's existence through absence or disturbance, a subtle dimming of starlight, a wobble in a star's position, a gap carved quietly into a debris disk. Direct imaging is different in a way that almost feels philosophical when you really think about it. It's the difference between deducing that someone walked through a room because you found their footprints left behind on the carpet, and actually watching them walk directly through the door with your own two eyes. TWA-7b is a planet we can genuinely point to, an actual location captured inside an actual image, however faint that single point of light might appear, something we know for certain is a real physical object out there in space and not merely a mathematical inference pulled from indirect data. Let that sink in for a second, because it genuinely is one of those moments where science quietly rewrites what we thought was possible. And if that idea landed with you the way it landed with me, this is exactly the moment to hit that subscribe button. As instruments continue to improve, both aboard Webb itself and aboard future observatories currently in active development, this ability to simply look directly at another world rather than deduce its presence indirectly through secondhand evidence is expected to become one of the single most important tools available for eventually finding and studying an Earth-like planet orbiting another star in genuine, real detail. For right now, TWA-7b remains a young Saturn-mass world, calmly orbiting a 6.5 million-year-old star roughly 111 light-years away from where you're sitting right now, tucked inside a debris disk that first tipped astronomers off to its hidden existence years before the telescope, capable of actually confirming it had even finished being built. It stands, by every measure available to us right now, as the lightest planet ever captured through direct imaging, and the very first new world the James Webb Space Telescope has ever found simply by looking. Astronomers are already applying the exact techniques refined during this discovery to search other young, disk-bearing stars for similarly hidden worlds tucked away inside their own debris rings. And every successful detection made at this particular mass range quietly makes the next, slightly smaller, discovery just a little more achievable than it was before this one happened. That is genuinely the exciting part of this entire story, that TWA-7b is not really an ending at all. It's a proof of concept, a demonstration that the ladder toward directly photographing an actual Earth-like world is climbable, one careful, hard-won rung at a time. Think about what that actually means for a moment. Somewhere out there, orbiting a star we haven't even properly studied yet, there could be a small, rocky, temperate world quietly waiting to be photographed the exact same way TWA-7b just was, using the exact same patient combination of debris disk structure, coronagraph engineering, and careful image processing that just worked for the very first time in June of 2025. We are Quite literally, watching the opening chapter of a technique that could eventually let us stare directly at another Earth. Not infer it, not calculate it from a wobble or a dip in starlight. Actually see it. It also helps to step back and remember just how young the entire field of exoplanet science actually is. The very first confirmed exoplanet orbiting a sun-like star was only discovered back in the mid-1990s, which means everything we think we know about. Worlds beyond our own solar system has been built in little more than 30 years. In that short window of time, the count of confirmed exoplanets has exploded from a small handful to nearly 6,000, and yet, remarkably, less than 2% of those thousands of worlds have ever actually been directly imaged. The rest exist only as data points, inferred from dips in starlight or tiny gravitational wobbles, never once actually photographed. That statistic alone should tell you how genuinely rare and significant an achievement direct imaging still is, even in an era when exoplanet discoveries have almost started to feel routine. TWA7b did not just add one more entry to that small, exclusive list. It fundamentally shifted what kind of planet belongs on that list in the first place, proving that the smaller, cooler end of the mass range is finally within reach. It's also worth understanding that this discovery does not exist in isolation. It sits inside a much larger ongoing push across the entire astronomical community to build better tools for finding worlds like our own. Ground-based observatories are already being upgraded with increasingly sophisticated coronagraph and adaptive optic systems, designed specifically to push direct imaging capabilities even further than Webb managed here. Looking further ahead, an entirely new generation of observatories is already under construction or in active planning, including the extremely large telescope expected to begin operations toward the end of this decade, and NASA's proposed Habitable Worlds Observatory, a mission conceived specifically with the goal of directly imaging Earth-like planets around sun-like stars sometime around 2040. TWA7b is, in a very real sense, a proof-of-concept discovery for every single one of those future missions. It demonstrates that the fundamental approach, using a debris disk's structure to predict exactly where a hidden planet ought to be, then confirming it with a coronagraph and painstaking image processing, actually works in practice, not just on paper or in a computer simulation. There's one more detail from this discovery that deserves real appreciation before we wrap up, because it says something important about how modern astronomy actually gets done. This was never a single instrument working alone in isolation. The initial clue, that mysterious gap carved into TWA7's debris disk, came from ground-based observations using the European Southern Observatory's Very Large Telescope in Chile, years before Webb ever got involved at all. Webb's own Coronagraph, the piece of hardware that finally delivered the confirming image, was designed and physically built in France, a contribution from international partners, folded into an already deeply international observatory. And the final confirmation required combining infrared data from Webb with earlier visible light data gathered from the ground, layering different instruments and different wavelengths together to build a single coherent picture. Modern astronomy, in other words, is rarely about one telescope doing everything alone. It's about patient, careful collaboration across instruments, countries, and years of accumulated data, all pointed at exactly the right target at exactly the right time. If this is the kind of story you come here for, one built on real, verified science rather than exaggeration or clickbait, go ahead and hit that subscribe button and turn on notifications, because there is a lot more of the universe left to actually see, and this channel is going to keep covering every single step of it. Drop a comment down below telling me what you think the next generation of telescopes is going to find out there, because honestly, after a discovery like this one, almost nothing feels off the table anymore. And if you know someone who still thinks we've never actually seen another planet with our own eyes, do me a favor and share this video with them right now, because after today, that simply is not true anymore.